Hello everyone, welcome. This is the makeup lecture of ECE451. ECE451. Okay. So last time we have discussed how to solve a system, right? We have a system. We use Laplace transform to solve it, right? System. We use a differential equation, summation a I y take is k y to the case order derivative k run from 0 to some n equal to summation bk. Here's the input to suppose r. Take case order derivative and k run from 0 to some n system. To solve, we use the Laplace transform. Then we can have a algebraic equation, right? Algebraic equation. Then we can have y of s equal to something, right? Then we use inverse Laplace transform. We have y of t equal to something. Yeah. Here the key formula is this one. Y take derivative to Laplace transform. We will have s capital Y of s minus y of 0. Okay, this one. So all these calculations you need to know what are the initial values. But here we have a special case. If we have 0 initial, y of 0 and y prime of 0, all of these, they are 0. Then what will happen? We only have this term, s times y of s, right? Here you look at the Laplace transform, right? Only this term, no initial values, they are zeros. So the things turn to be simple. We can have, see, this is equation 1. The 1 by Laplace transform, we will have summation a to the a of k, and here is s to the k times y of s, and equal to here summation bk. This is also s to the k, then times r of s. So we can have y of s equal to, this is a summation of all these bk s to the k terms, and the denominator is this side, this part, right? So summation a k s to the k. Here k run from 0 to m. This is k run from 0 to n. Then times r of s. So we have the output. It is just r of s times this part. So this is very good result. You can select a different r, then just times these, you can have y. Then you can find the inverse Laplace transform. You can have y of t, right? You can have y of t. Alright, this part we give a name for it, because this part can be used anywhere, right? No matter what is the input, you can always use this one, right? This one times the input, you have output in s domain. So we call these as a transfer function. Transfer function. We can denote it as like h of s, or maybe g of s, f of s. That's your choice. Alright. Okay, suppose now we have h of s for the transfer function. Then we have y of s equal to transfer function h times input in the s domain, right? Or h of s equal to y of s over r of s. We can use the second to determine what is h of s, determine the transfer function. You can select some r, make the like a symbol R, and here is you get a Y, then you have H of S. Then you want to find the different input, what is output, you use this. You already have this, right? How you already have the transfer function. So transfer function time input, you get output. It's a very convenient tool. And the transfer function, and for transfer function, you can just start from the system equation. You know these coefficients, right? You put it here, right? AK, BK, AK, BK. Yeah. Like we have example, we can check an example. Y is 3 derivative plus 2y 1 prime plus y equal to 4r with 2 prime plus 9r. Then we have transfer function. Is, I give a letter still, I use H, okay. This is here's 4 with S squared because he is 2 prime plus 9, just 9, no prime, right? No derivative. And here's S cubed, right? Because he is 3 prime plus 2, 1s, and plus 1. That's it. Now you give different input, you times these, you estimate, then you can have Y of S. Okay, then we can consider some special case. One, the impulse response. Third of t is the input. We go to the system. Now we can use H of S to represent the system, because when you determine what is H of S, you can always find the output, no matter what is the input. Right? You can always find the output. Now the output Y of t. With this third of t as input, third of t, right? Third of t. What is the output? Okay, we have Y of S is H of S times the Laplace transform of the input. Well, remember this? Laplace transform of that, it is 1. So this is just H of S. Okay, so we have Y of t, it is the inverse Laplace transform of H of S. You can also write this as H of t. If transfer function is capital H of S, then the impulse response, it is just the inverse Laplace transform of H. It is a lowercase h of t. Right. Alright. This is the impulse response. And the second one, we consider the step response. So here is a unit step. Now I put the S here. Unit step t. Right? It looks like these. Here's 1. Right? We still denote the system as H of S. Then output, I still use Y of t. Okay, then in S domain, Y of S is H of S times the, okay, this is capital U S of S. This is 1 over S times H of S. Yeah, that depends. You need to do some calculation. If you know what is H of S, then you by the inverse Laplace transform, you have Y of t equal to something. Yeah, depends. Of course, here both we require 0 initial. Also 0 initial. When we say impulse response, we suppose the input side is we suppose the system with 0 initial. Here is also step response is always for the case 0 initial condition, so we can find them in this way. Yeah. Now we can have a look how it looks like. I have my lab here. looks a little bit strange. Okay, so we have, we'll let S equal to, just a notation. Alright, I get S. Okay, then we give a system h of t and a capital H. H of S. H of S is the transfer function. No, I already have S. So we start from a simple case. It's 1 over S plus some number like 2. Actually this one. Then the step response will be simple, right? Impulse response will be simple, just inverse of these. So h of t will be e to the negative 2t, right? E to negative t. But we can show it here. We just type impulse response of this h. It will show you a graph. E to the negative 2t, right? E to the negative 2t. And we can also see what is the step response. Step response will be this one. The input is step. Start from 0, it will jump up to 1, here, right? Then it's a step. The output is also kind of step. Jump from 0 to 0.5, but this jump is gently, gradually increase to 0.5, not directly jump to 0.5. And we can also see, like we use a different input. I select the time t equal to 0 with a step 0.1 until like 10. I give a time duration, and the input signal, suppose that is r of t, is r. R is a cosine. It's just cosine t. Alright, cosine t. I have r equal to cosine t. Then output is y, which is we use this command, LSIM simulation, linear simulation of. I need to put system is h, and input is r, time duration is t. Okay, then we have a r. We have a y. We can plot what is plot t and okay. I plot both t and r, and the t and the y. Alright, we have two figures. One is start from 1 and going down to -1, so this will be cosine, right? It's the input. This blue one is the input. Then the green one start from 0, increase gradually, and finally it is also will turn to be a sinusoid. It's a wave. Yeah, just the beginning is not so perfect, but finally it will be a kind of a wave, similar with the input, but amplitude changed and like 0.4, and the phase is also changing, right? Here's the big sorry. I got some cough. Here's a 0, peak value is t0. Now the peak value at a t nearby 1, something like that. And here is also similar. So the output, when time is big enough, it is also a wave looks very similar, or maybe just equal to a sinusoid, but with a different amplitude and different phase. The input is sinusoid. Okay. So these are the example for the first order. We can also see the second order. I use a G G equal to second order system. I use I use this one. Last time we have studied in the class, right? It's S squared plus 2 times S plus 10. We have different G, different system. Then what are the impulse response? Step of G, also similar. Step response of G. I see this one. You see, start from 0. Is finally you can think this is also a step, right? The output is input is step, unit step. Output, this is also a kind of unit step, but with some increase, then overshoot, and going back to 1, and then up and back, and limit is just 1. Things like this. This is a step response and impulse response. Impulse response of this G. Is this one. You have a pulse, and then going down, but with some oscillation, and finally tend to be 0. Yeah. Okay. And we can also see if we use R as input, this one, but now the system I use GS system. You can see it look like this. Alright, it's the impulse response. Okay, these are the graphs, how they looks like. Then you can also solve them, right? Yeah, you can save them. No. You can solve them, use formulas, right? Use formulas, and the result will be some combination with some exponential power, but with complex, like this one, with complex poles, and finally you can change them to be the cosine or sine. So the way the final answer looks like this, right? You have a kind of sinusoid, but the amplitude is decreasing. Right, the first peak, the amplitude is large, and then the amplitude tend to be smaller. You can see this is kind of sine wave, right? Yeah. Okay. Now we go back to here. Now we consider some details about the second order system. What is the feature of the step response? So we consider the step response of second order. We say this is a prototype. Prototype system. The transfer function of this system will be transfer function. It will be h of s equal to some omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is also a term in the Laplace transform table, right? Okay, then the step response looks like we just have it, right? Looks like this. Okay. Here we want to know some more details about this step response. The first one, we want to know the poles of this one. Poles of h of s, poles of the transfer function. Then they will be numerator, let the denominator equal to 0. Then you solve it. You can have P1 and 2 poles will be negative zeta omega n plus or minus square root of 1 minus zeta squared times omega n j. You can also move the omega n outside, then times negative zeta plus or minus j times square root of 1 minus zeta squared. You can also write in this way. You're writing this way. And in the graph you can see, so here's a negative zeta omega n, something like this, and here's a square root of 1 minus zeta n, zeta times omega n, zeta squared, 1 minus zeta squared times omega n. And the length of these, it will be omega n, right? If this takes square, this takes square, you add them together, then the zeta square omega n square will be cancelled. You already have omega n square that takes square root, so it is just omega n, right? Omega n. And then we have a theta. This theta, this angle theta equal to arc cosine of zeta. And this theta is very important because the output, this one, in the output, we need this theta. And remember last time we checked the table, right? Check table. It is I put it here. Step response, I give a name. I say it's y of t. Y of t will be 1 minus, here's e to the negative zeta omega n t, right? Over 1 minus zeta squared. And here will be sine. This is omega n times square root of 1 minus zeta squared t, and plus theta, right? Plus theta. Theta is just this one. Theta is just this one. We have this. We have this theta. Theta is just this angle. So you see, this pole, it gave us all the information in the formula. Zeta omega n is this value, right? Zeta, this is negative zeta omega n, right? Negative zeta omega n is this value. And this one, this frequency, is just this number, right? This number. So the real part and the imaginary part, real part and the imaginary part of the pole. And this angle, it is just this theta. Angle, it is just this theta. And 1 minus zeta squared, it is it's this part. You can consider this is also, you see, this length, square root of 1 minus zeta squared is this length. This length is what? It is sine theta, right? This is theta. This is sine theta. This is sine theta. Sine theta, right? So the pole of the edge of S, it gave us all the necessary values in the step response. Now, of course, we need a condition. We want we really have the complex pole, so zeta should be value smaller than 1, absolute value. We need this condition. If this is larger than 1, then this one will provide us a real poles. This is for the complex poles case. Actually, 2 poles. Another pole is here, right? Another pole is here in the other side. Here is minus j, with a negative imaginary part. Poles. Okay, and we have some names. Okay, I gave the graph again. I still needed the graph. Okay, we need some names. You look at the output. Actually, it is a sine wave, right? It is a sine wave. The amplitude of the sine wave is a decrease. Yeah, it's here. This is the amplitude. Amplitude of this sine wave, it is this decreasing. When t large, this will be small. So we call this is a kind of a damping. So we have we call this zeta as a damping ratio. Damping region, damping region. And zeta times omega n is also damping factor. Right, both for the damping. If they are small, then this one will decrease slower. Decrease but not so fast. If this is large, it will decrease quickly. Right? And then omega n, we call this is a frequency. It's a undamping. Damp is a undamped natural. This is natural frequency. Yeah, natural frequency. It is not. Looks like not really frequency, but we call it natural frequency. Undamped, and then the omega n times square root of 1 minus zeta squared. This is the real frequency in the solution. Okay? Here, this one. We can also denote it as just one letter. It's omega d. Yeah, we can denote this as omega d. It is a frequency. This is a damped frequency, right? That is undamped. This is damping. Just frequency. This is really a frequency. So this is a sine wave, but the amplitude is damping is smaller and smaller, decreasing. Right? Yeah. Okay, we have some names. We can have more things. So we still look at this one. So the wave amplitude is smaller and smaller. So after a while, suppose here, this will be just like a 1%. The overall, actually here will be 1. Here will be 1. You look at the output solution equation. It's right here. Right, 1 minus this part. So when t large enough, this amplitude tends to be 0. So this part is 0. You only have 1. The limit is 1. Right? So limit is 1. We call this a steady state. Right? Limit is 1. And here we want the after a while, the difference between the signal with the steady state with this one is less than 1%. Then this time we call this is a setting time, TS. So setting time or setting time. Yeah, so same meaning. Setting time, TS. So how to find this TS? It's amplitude. So we need the amplitude smaller than 1%, right? This amplitude is this one. So we want this whole thing smaller than 0.1. But this one is harder to calculate. You see, you have exponential power, also have a square root. You want determine this t. It depending zeta square, depending on omega n. So this is not so easy. So we have a approximate way. We use this way, TS. You see, when t larger than or equal TS, the y of t minus 1, the absolute value, or smaller than 1%. Right? This is setting time. And we can solve TS find approximately we just use this part. Is e to the negative zeta omega n t absolute value smaller than 0.01. With this way. Now this is approximate. By this way you can take a lot. t equal to log of 0.01. Actually, this one you can find that it will be negative 0.4 something, 4 point something. I forget. Log of 0.01. Oh, no log. Log. Yeah, 0.46. Yeah, 0.46. 0.46. So we just use 0.46. That will be fine. Uh, 4.6, not 0.46. 4.6. Like this. Then we have t equal to for the 6 over zeta. This one. Zeta times omega n equal to approximate. I put the dot means approximate. So we have a setting time. That means like when you start a system, you just turn turn it on, it will run like a home. After a while, it will go smoothly. Right? In the beginning, you have some time the system might be shake, maybe overshoot. Right? This is After a while, it is smooth, and that smooth state is start from TS, start from the setting time. Now, of course, this formula just for the prototype second order system. It's setting time. Alright. Then we have another time. This is rise time. Rise time. What is rise? You see, the response, step response, it is rising, right? Coming up and down and up and down, like this. So start from 0, finally reach 1. So here we give two locations. Here's a point 1, here's a point 9, and we have 2 time. Right, 2 time. The time between these two, we call this as TR, is a rising time, rise time TR. So what is the meaning? Start from here, the system state. The output to give you a 0.1, the value is 0.1, the feeling is like, oh, it's running. Before that, the system maybe you have some value, but in your sense, maybe the system still, it's waiting. It's a kind of delay. It's very small, you can't feel it. After this, you can see, the system is a startup. And when it reach 0.9, almost done. So we use this time, we call this time the TR as the rise time. This value is it is used in the industry. People like this time. So we need to give the value of it. So what is this one? You still need to look at the formula actually. So you need to solve. Make this part to be a value, very close to 1. When t is 0, this is 1, and this one it is just this one. So when t is 0, this is 1. This part is 1, and then when t increase, this one will increase. So from 0.9 to 0.1, and then you get that 2 point and take the difference between that 2 point, that 2 time. Then you can have this one. So it's a it's a complex calculation, and this calculation we do not have general formula. You can just by experiment, like a kind of experiment, you take different values of zeta and omega n, then you can find the rising time. Then you have corresponding, because you have calculate, you can have some you use some omega n, some zeta, and then you have TR, right? You have some values here. Then based on these values, you try to give an approximate formula. Okay, so here I just give you the formula here. We have TR close to 1.8 over omega n. That means this rising time, when zeta is changing, you use a omega fixed, just change these. The rising time almost the same, change a little bit. So the final answer here, you only have omega n is fine. Omega n is fine. And then omega n, looks like when omega n is large, this TR will be small. So you choose large omega n, it will start up quickly. And when the omega n is large, when the omega n is small, it will increase gently, slowly. Yeah, say it like that. And yeah, close to this one. So we have this formula. You just remember this formula, will be fine. All right. The next one, you see, the system start up, reach 1. Actually, 1 should be the steady state, but the system will keep going up. So reach your peak value, and then falling down back to 1, and go back to this, go down back to the smaller than 1 part, and up and down kind of oscillation for a while, right? So this peak value is very important. What is this peak value? So we have the peak value, we need to solve y prime of t equal to 0. Right? We need to solve y prime of t equal to 0. Now what is this? Okay, we can have a look. Y is here, right? We take a derivative, then this 1 cancel. We only have this, and this minus doesn't matter, right? So we just need the derivative of this part equal to 0. Okay, then we have 2 parts. So we take derivative on the first part. We have negative. Oh, okay, I keep this negative. Then here is just a plus, right? Plus 1 minus zeta squared. I still have this 1 minus zeta squared, and this is a zeta omega n, the negative cancel, and e to the negative zeta omega n t times this sign. Yeah, I use WD for shorter, right? T plus zeta. The first term, we take derivative on the exponential power. And second part should be plus this thing, but this is minus, so I put minus. And I keep these. It's okay, I'm writing this with 1 over square root of 1 minus zeta squared times e to the negative zeta omega n t. And the sine, take derivative, we get cosine. But here, cosine of omega dt and 1 omega d in the front, and plus c. Right, look at these. Okay, we can cancel this part. Right, we can cancel this one. Equal to 0. We can cancel this one. We can cancel this one, and also cancel this one. Right, those contain the exponential power. So finally we have this one, zeta omega n. Omega n we can also cancel here. Omega d. Omega d is omega n times square root of 1 minus zeta squared. So this omega n can also be cancelled, right? This omega n can also be cancelled. So after we cancel these, we have zeta, only zeta left, right? The sine of omega dt plus zeta minus the exponential power cancelled, this one cancelled, the omega n cancelled, we have 1 minus zeta squared left, and times cosine omega dt plus c equal to 0. Okay, this one looks not so complex, right? So this one equal to sine equal to cosine. Then there will be the tangent, right? The sine over cosine. Sine over cosine is the tangent, right? Sine over cosine is the tangent. We divided this, and equal to this one over this one. Tangent of omega dt plus c equal to which one in numerator? This one in numerator, right? Cosine here. So it's the square root of 1 minus zeta squared over zeta. You look at the graph of the pole. Right? Here's a zeta omega n, and this is square root of 1 minus zeta square omega n, and here's a theta. Now what is this? This one over this one, the tangent. Actually, this is tangent theta. Right? The tangent theta. So we can say omega dt equal to plus theta equal to just theta. Alright? We miss something because it's a triangular, right? So we have a period. What is the period of this tangent? It's 2 pi or pi. Tangent the period is pi, right? So plus k pi. This is t. Okay, so omega dt equal to just k pi, and pi k will be on the integers, right? 0, positive, negative 1, positive, negative 2. Out of these, then we have this t is pi over omega d times k. So look at the graph. Here I have graph. We have this point, this point, this point, this point. Actually, this is a sign, right? So this is like a half of the period, half of the cycle. It will be pi something. So here is a pi something, right? If it's a 2 pi, then the whole cycle. This is pi over omega d. Actually, pi over omega d is a half of the cycle, and every half cycle for different k, we have a point with derivative 0, derivative 0, derivative 0. This is derivative is also 0. But we only need the first one. First one gave us the peak. So k equal to 1 gives the time, the peaking time, peak time. We write it as Tp equal to pi over omega d. Pi over omega d. I give it another graph. Pi over omega d. This is a Tp. And this will be peak value Yp. Right? This peak value Yp. And the Yp will be, we need to do some calculation. Do we have time? 42. I think I have that peak value somewhere. Sorry. Before I come to here, I have the peak value. Sorry, disappeared. Put the peak value somewhere. I see. Okay. Yp equal to 1. Now we need 1 plus exponential power negative pi zeta over 1 minus zeta square. Actually, denominator is still need omega d, but we have omega n in the zeta omega n in the numerator, so they cancel the omega n. So we get this one. So e to this one. Okay, this is Yp. This is Yp. Alright. And yeah, you can also plug in. You know what is Tp, right? You plug in, then you calculate. You plug in the system in the output. Yeah, you plug in the output. Tp, right? Tp you put it here. This is a pi over omega d times omega d. They cancel. So this is a pi sine pi plus theta. Sine pi plus theta. And it is just this one. They cancel. You just have this term. So with a negative, because the pi here. So 1 plus this part. 1 plus this part. This part now t is Tp. So Tp. So this one times Tp, you get this one. Yeah, it's not too complex. So we have this one. This is peak value. Peak value. of the step response. And sometimes we want this part. We call this overshoot. Overshoot denoted as MP, which is 1. Is YP minus 1. Over. How many over this 1? Right? Is 1 over 1. So this is just the exponential power part. E to the negative pi zeta over 1 minus zeta squared, take a square root. Okay, so we have this is MP. It's MP. Alright. And sometimes you can times like 100%. You see how many percentage overshoot. Like if this is a 0.1, you can say this is a 10% overshoot. Alright. Let me see. For step response, the special values. Yeah, all the values we already have. Yeah, I think they are the values we want. And and for the for a system, if you have a second order prototype system, then you can have all the details about the step response. And in the work to design the system, sometimes you have some requirement, like you want MP is not over, for example, not over 10%, or you want the setting time is less than 1 second or something. Then you know, okay, you give some parameter in the system so that you can change the parameter, and you calculate. You follow this formula. You can calculate to find like what is the setting time, what is the rising time, what is the peak value, and all these values were in terms of that parameter, right? You have a parameter can change in terms of that parameter. Then you want like MP equal to certain smaller than certain value. Then you know, okay, which kind of parameter you can choose. You choose different parameter, this MP will be different, right? You choose the parameter, make the MP satisfy your requirement, or the setting time satisfy your requirement. Yeah, so these values are very useful. Yeah. Okay, that's all for today. Then see you in the class next time. Yeah.